Hello, welcome to my presentation, Power Analysis or Side Channel Analysis for Cheapskates. So my presentation is all about how we can do side channel analysis at a much lower cost and with much smaller equipment than you'll normally see. So all the equipment I'm demoing fits in this little box here. I'm from Dalhousie University in Halifax, Nova Scotia, Canada. And here is a map of Canada, in case you're not familiar, and Halifax is just on that little tip there, so we're right on the water. My funding comes partially from Dalhousie University, OZ Optics, as well as there's special thanks to Cryptography Research Inc. for supporting some of the boards I'll show later, some of the more advanced SASEBO boards, as well as thanks to all the sponsors of the Blackhat Abu Dhabi conference, of course. So what I'm going to talk about, the way forward, is I'll look into what is side channel analysis, and I'll try to give you a bit of a tutorial on this, a fairly quick one. If you've already have some idea of how this power analysis works, you'll probably get more out of the rest of the presentation, but I want to give everyone a chance to sort of understand the low-cost hardware part of this. Next, I'll be talking about First Attack. So this year, First Attack is really a demo of all the hardware and software I've created here and is available on the CD. I'll talk a bit about specifics of the attack, waveform acquisitions, probe types, amplifiers, how we measure current in real devices, and there's a few loose ends, a few boards, and any questions in that time. So, what is the side channel? So, the answer to that is, well, what is the main channel? If we have a cryptographic device, the main channel is, for example, the serial I/O or I/O pins that we're sending information saying, please encrypt this, and it says, okay, encrypts it and sends it back. The point is that over the main channel, you can't figure out this secret. That's the whole point, right? If you have the plain text, you have the ciphertext, and that's it. You get those two, you can't derive the secret. So the side channel is saying, well, that's true theoretically that there's only one way to communicate with the device, but maybe there's other ways to communicate with the device that probably weren't intended, probably either manufacturing defects or some aspect of how the device was created. And one side channel, there's more than, just the power side channel, but all I'm talking about here is the power side channel, and this is looking at how physical properties of how any silicon device is sending data around, how we can sort of look at those physical properties to see what data is being thrown around inside the integrated circuit. So this will make more sense when we look at a device. So here's some random device, Crypto Pro 9000, world's most advanced 4-bit processor. So we have a 4-bit machine, and when you look inside it, you'll have some memory connected to some other parts. So in this case, the memory could be registers or RAM or whatever program code even. What we're talking about is RAM, basically, so registers and such forth. And it'll send the data to another part that's doing an operation. So here we have an ALU, arithmetic logic unit, that'll do adding two numbers together, loads one number, loads another number, adds them, puts the result somewhere. So this is a very basic design of any real digital embedded circuitry. And how this data is sent is normally there's a clock that's distributed to everything. And the clock makes sure the device marches at the proper beat. On every rising clock edge, new data out, new data out, new data out. So this is sort of cracking the whip of the digital slave driver, you could say. So here, let's look at two of the data lines on a data bus. Different devices could have different widths of data bus. If we have a small microcontroller, often this means an 8-bit data bus, but your larger computer will have 32-bit integers often, which means a sort of 32-bit standard data or 64-bit. And if you have really odd systems or special designed hardware, this data bus could be wider too. Anyway, so the data bus is effectively physically wire, physically lines. And if it's at one voltage, 0 volts, which we call a low, we need to then set it to, say, a high. So going from a 0, which is shown in this diagram, this sort of lower point here, to a high, which occurs right at the clock edge. And how do we do this? Physically, it takes a tiny bit of power, because you have to effectively, setting the voltage, you can think of it loading electrons onto this wire. So once we set it, it'll stay at that voltage effectively. I mean, if you're familiar with electronics, you can think of the little bit of wire. It's a tiny capacitor effectively. It has a little bit of capacitance, so you set it to some value. And to change it to that value does take power. Once it's at the value, it doesn't take as much power to just keep it at that state. So every time we change, it takes power. This is why as processor speeds go up, the amount of current typically goes up as well, because it's switching more often. So it's changing data line states more often, which means it consumes more power. So when you clock a CPU at a lower frequency, the power consumption of it goes down. So, if you have a little crappy netbook and it's set in low power mode and it's really low performance, you can barely watch your YouTube videos or whatnot. Whereas if you set it in high performance mode, it drains the battery faster, but it's noticeably more responsive. So anyway, what we care about is the fact that right at that clock edge, so at the first clock edge here, we can see the power is going up. There's a bit of a tick right at that clock edge when two data lines switch. By comparison, if no data line switches, there would be no real tick there. This is obviously a very simplified diagram, but you get the idea. Likewise, or if lines are switching down, it'll have to, what that sort of jump down is indicating is that the power it's being consumed, it's actually using it to set the line from high to low. So based on this sort of little amount of power it's consuming, you can get an idea of what is happening inside the device. So let's look at how we can use that to make a side channel attack. So a side channel attack means we have A and B. This is the main channel, so plain text, ciphertext. At some intermediate point here, C, we have this secret that you might be able to derive. So obviously, if we just knew A and B, the point is you cannot figure out the secret key. If you knew A and C, you could figure out the secret key, or B and C maybe, depending what it is. The point is there's these intermediate operations that aren't as secure as A and B. So sort of to see, again, everything here seems pretty abstract. So let's look at a really specific example. Let's look at a 4-bit machine, and that 4-bit machine does only one operation. It adds a plain text input, and it adds to that input a secret number we don't know, and the output just goes away somewhere. So, in the crypto operations, what we're considering is that the output could go on to other stages, or it could be that it's physically not available to us. In this case, I'm just saying, you can't read the output. All you can do to figure out the secret is input data and measure the power. And what we're going to do, the process we use, we input a whole bunch of different data. This is all 4 bits, remember, so you're limited 0 to 7. So we'll input the different data. Now what we can do is we could guess what that secret number would be. Remember, we can't see the output in this case, I'm saying, so we couldn't even check it using the regular method to know if we're right or not. So what we could do, though, is we could look at a single bit of that 4-bit output. So I'm going to concentrate on bit, one of these data lines, so bit 0. And I'm going to say, okay, well, if the input I put in, I know for sure I put in a 4. If the hypothetical secret number, if the number was 2, say it was 2, I don't know what it is, bit 0 would be 0. If I put in a 7, and again, I'm assuming it's 2, then bit 0 would be 1. And we can go through this for each of the operations. So remember, I'm just talking about a hypothetical secret number. I've just said, hey, it's 2. I'm making this up here. But what I could do is, remember, every time I've put in a plain text, I've been measuring the power that the device is taking to do this addition. And I split all of those into 2 groups. So I take one group where, for example, I'm saying, hey, the bit's 1 in this group. So in this power trace here, this intermediate value is 1. In the other group, this power trace, I'm going to say, hey, that bit is 0. Because I input a lot of different plain text, remember the other bits that I didn't target, I only said bit 0 is 1 or 0. The rest of them could also be switching. But over time, they're obviously just going to sort of average out to 0.5. Half the time they will be, half the time they won't be switching. So if my hypothesis was correct, what I would expect to see is actually a major difference between these 2 sets. So if I average out the sets. And why this is that if I'm correct, at one location, when it's doing, when it's outputting the number onto the data bus, what I'd expect to see is that I've added up a whole bunch, like 100 or 1,000 of these power traces, where bit 0 is 1, and that's one set, and there's a whole bunch in this other set where bit 0 is 0. And if I'm correct, then I should expect to see this, difference between the 2 sets. Whereas the rest of the time, it should average out to sort of the same if there's enough of them. If I'm wrong, I don't expect to see this major difference between the 2 sets. So then, all I have to do is I measure the power, and I measure, inputting data. And I have this group of traces. I then guess for each of in this case, 16 possible hypothetical values. I do this division. So I take the same traces, and I divide them different ways, based on if the hypothetical value is 0, and I input 4, this is 0. If I input 7, and this is 0, this is 1, 2, etc. So, in this case, the division will be, for those 2 first ones, the same. But you can see how what I'm doing is I'm just trying every possible hypothetical secret number. One of these hypothetical numbers should give me the biggest difference between the 2 sets, meaning my answer was correct. So there's some other advantages I'll show you in sort of 2 seconds here, so hold on if you're saying, in this case, if this was 0, one thing that's odd is that if this hypothetical number is 0, all of these bit values are going to be the same because it's still going to be 1. If 6 plus 0, it's still going to be 0. 5 plus 0, it's going to be 0. So that's no good because if the hypothetical number is 2 or the hypothetical number is 0. When we attack crypto algorithms, it's what we're looking for is not to attack something like an addition that obviously, hey, this would not work for that exact reason. So we'll be attacking other algorithms like the S-box, which doesn't have that property. So if you want to write out what is differential power analysis in steps, it's just what I said. Basically, we input many plain text, measure the power, target a single bit in each byte of the key. So I'm going to look at, bit 0 in every byte. And then I just make a guess of the key byte. So one thing you're going to next say is, that example you just did was a 4-bit device. A, that's stupid because you could guess that in 16. But B, we still have 128-bit keys, so where does this help us? Because we can't guess 128 bits. The point of DPA, or all of these side channel analysis, is that we're going to be targeting algorithms that at those intermediate values, you can easily split off from the key sort of 1 byte at a time. So let me go back here. When I talked about C here, the point is that the secret key, when, for example, AES is running and it's working with 1 byte at a time and doing operations on part of the plain text with 1 byte of the key at a time, Because of that, at C, it's not done the operation yet. At C, though, we can guess a single byte of the key. So just one byte, which is only 256 possible guesses. So to really show you, give you the full view, let me show you Python code for doing the GPA attack. And this should hopefully make the most sense. It's sort of hard to make analogies for some of this when you can just really look at the code and then see it. So what you can see, hopefully, is that there's an outer loop here that's just guessing over 16 bytes. So inside here, everything we're doing is just going to go through all of the 16 possibilities. So for each byte, I'm then going to guess from 0 to FF. So all of the 256 possibilities for that key. And how we do this is our hypothetical value is we're just taking the output of the S box. So that what we're doing here is just attacking the S box. So I'm saying, as part of the AES algorithm, I know what's going to happen is there's going to be the plain text, and it's going to be XORed with this hypothetical, this key value. Again, key here is the hypothetical. I don't know what it is, so I'm going to say, well, what if it's 0? Then the output of the S box would be this. What if it's 1? The output's this. That 2, this. The S box is very nice to attack because it's nonlinear, so we don't have this issue I had earlier where I said, hey, 0 and 2 is giving us the same value for bit 0. So we basically won't get this property. And when you do the attack, you'll get much nicer results. So I get a hypothetical value. Again, we just see, hey, is the target bit 1 or target bit 0? If it's 1, I add it to this group of traces. If it's 0, I add the current trace to this other group. And then we just do the same thing I was saying before, average the two, find the difference, and in this case, I'm just finding the maximum biggest difference and saving it. So this code is very, very simple, but it works. And what I can do to convince you of that is show you your first attack. So should you attack a smart card? That's always a sexy thing to attack. And if I open up my kit here, I have this smart card in there. This is an XMega card. So these are programmable smart cards that just have generic microcontrollers on them. They're not crypto specific at all. They don't have any hard, crypto hardening or anything. This is not your bank card. This is 1,000 times less secure than anything you'd expect to see in real life. So if you wanted to attack a smart card, you can buy a smart card reader off eBay. So here I have just a generic smart card reader. You can insert a current shunt, and you can pull out some other signals you'll need, like the clock. In this case, I'm cheating and using some other lines for synchronization, but you don't need that. Close it back up, and you sort of have this nice little smart card reader with a connector on the back. So if you do this, you can then connect it up to your capture hardware, and on the left there, so this is the OpenADC, this is the capture hardware I'm going to be demonstrating and going to be showing you later on, and this is the sort of the low-cost capture hardware I've been talking about. So that's one way to go. But what if you wanted to do this cheap? So the downside here is that you need that smart card reader, and you need all this other crap, and you need often you'll use a special programmer, although you can get away with just generic AVR programmers. So then here I have an example of a cheapskate smart card reader I've made, and it just connects using a USB to serial converter. And we can wire it up to that ADC board, the OpenADC, and do the attack on that. So to give you a closer view, this is the smart card reader itself. So it's just USB board, and there's a few small parts. So I'll go through both of the examples first, and then sort of show you a demo of the different target hardware. So the one thing you have to realize, though, when I say a smart card, is it does have a nice sexiness to it. You can say, ooh, I'm attacking a smart card. But this smart card is an Atmel ATmega, as it says right on the card, ATmega 163. It's not a crypto smart card. There's nothing special about it. It's the exact same thing as attacking a regular microcontroller that you just plug into a breadboard. So what I recommend is that if you're interested in getting into this, you just don't even bother with the whole smart card thing, because you have to, get a special socket, and it's hard to find these smart cards that you can program, whereas there's tons of microcontrollers on DigiKey. You can spend $2 and get one delivered to your house. So when you do this, it looks very easy. So here I've built a circuit on a breadboard, and I have a AVR microcontroller in the center, and I have some stuff like I have the trigger signal going off here. I have this shunt resistor here, and this is what I'm measuring the power being consumed by it. I have a crystal here, and this is generating a clock signal that's not there, sorry. This line here going behind it is the clock. And there's some power supply stuff coming in you can't see, and this is the serial, so this is the main channel, you'd call it. What I have here is that what I showed you, except that what I showed you doesn't travel well because it's liable to break easily, as you can imagine. So there's a PCB version of it, and I've just soldered everything down effectively. All the schematics for everything and photos are in the white paper. So what's involved in making this? If you're interested, not too much. There's a regular AVR microcontroller, some various capacitors, resistors. The main thing you need is the capture hardware, typically an oscilloscope, but I'll show you some cheaper options. Serial USB adapter. You need clean power supply, which I cheat and I take it from USB, which isn't too clean, but I show you how you can use that. And the final thing you do need for these is you need a way of programming the microcontroller of your choice. I'm using AVR. You can get AVR programmers pretty easily, pretty cheap, eBay if you want, or DigiKey, I believe they're $30, eBay they're $10 type thing. So nothing that is difficult to get and is going to cost you that much. Again, see the schematics in the reference material. There's not a whole lot to it. So once you have it working, what you should see is you can use the serial port and just send it messages. So here I've loaded a key, I've sent a plain text and get a response. So the first thing I'm going to do here is actually plug in some of these devices while I'm talking. So if I get a USB cable, plug it in here. So that's just the serial adapter. And first, for example, if I just plug in the board, so I have this terminal emulator here, and if I send it a plain text, and there's a different key loaded by default, I send it a plain text and I get the expected response. I know that that's the expected response. So the next thing you'll want to do is characterize. So what I've done here is it's described in the white paper. You'll want to verify your environment is pretty clean. If you have a lot of noise, this is not good. So some of the cheapskate aspects of this mean you have to be a little more creative, and you have to test stuff a little better than, if you buy a nice board that has perfectly clean power supplies, you won't have to do anything. So here what I've done is I've connected this just the OpenADC, so the capture firmware. I've connected it only to the power supply. I have the AVR microcontroller, for all intents and purposes, isn't even hooked up. And what I've seen is that there's a lot of noise here. This is very bad. This would ruin your results effectively. So in general, you can just put some filtering on it. Normally you filter with a capacitor, which helped a little bit, you can see, but it's still these are bad, these sort of ripples. So I then add a larger capacitor in parallel, so there's still this ceramic cap. Add an electrolytic capacitor, which helps. And finally, I add a 100 ohm series resistor. And that has made it quite clean, as you can see. So that's what the schematic looks like. So we have a resistor, which is forming sort of a low-pass filter, and then a series of capacitors. So when I want to measure the power, then what I'll do is insert this shunt. The value of the shunt depends a bit on the device. If it's not taking much current, typically this means it's a more recent microcontroller. You may need something higher, like 100 ohms. If it's older, I mean, for my Smartcard device, I'm using like 30 ohms, I believe, because it's an older microcontroller, it takes more current. So I don't need as big a value there. So once we have that, we can continue to do a bit more characterization. And by a bit more, I mean we now are actually running the attack measurement mode, except we're using this persistence mode. So persistence mode is overlaying the results multiple times, and I'm inputting the same fixed plain text. When we do that, what we expect to see is that if you're inputting the same plain text, you hope to see very similar looking results. So now, once that's, again, you're sort of verifying, and if you don't, you can go back and say, was there too much noise? Is there an issue? Is there a problem with the capture hardware itself? If not, you can go ahead and acquire. So acquisition means we set up the device. So this is this AES Explorer. This is open source. Again, this is included on the CD. You just have to install some of the Python libraries and the stuff it depends upon. And in the background here, what I'm going to do is plug together my OpenADC and plug it into this computer so I can really show you the as promised live demo. So I'll connect power lines up. And while I'm doing this, I'll just tell you a little more about what you can do once you have these traces. So once you've acquired a number of traces, it writes them to, right now, and you can modify this obviously, it's using text files, and you can import them to something like MATLAB if you have that, which there's a number of various other example sort of attacks online. But if you don't have MATLAB, what I've created here, and this is something that will be expanded upon later, is a very, very simple DPA attack. This DPA attack will just output the most likely bytes. It doesn't even give you a graph or anything pretty like that. So there's an example of running the DPA attack, so that's the correct key. So that, sure, I've got some pretty pictures. Let's look at real life. So if I run the capture software here, and here I have obviously you can't see it in this version of the presentation, but I have the PCB board connected up. So this means what it's looking like is this is hooked up. So when the application opens, it looks something like that. Try to make this as big as possible. So I'll connect to the OpenADC, which I know is on COM22, and I'll also connect to the target board. So this is controlling both. And assuming everything's worked, if I hit capture 1, you'll see a screen like this. And I'm going to zoom in here a little bit. Let's capture again. So we now need to change the trigger, so I'll trigger it on the rising edge. And if the trigger is disconnected, when you hit capture, it'll freeze because it waits forever. That's a bit of a bug in the current version. So I'll increase the gain here. And oops, that's far too high, so we decrease the gain a bit. How much you need depends a lot on, what is the device, what is the shunt resistor value, stuff like that. So there's no one answer to this. All right, so there we go. So what I want to do now is switch from internal to external clock, which means the measurement becomes perfectly synchronized with the device under attack. This is because we're using the clock of the device to do this attack. So if I just hit capture here, and you can also do stuff like there's this phase adjust, which lets you, and I'll explain a little more about this, but it adjusts when the measurement itself is taken in the clock cycle. For some boards, this actually matters a lot. For this one, it doesn't really. So what I'll first show you is a little bit, if I want to say zoom in on from 1000 to 1500 here. Let's get a little closer to 1200. If I hit capture, so we can see when I'm talking about having a persistence mode, I can enable two options here, persistence mode, and the other thing, this version, there is fixed plaintext. So this is saying keep the same plaintext every time. So when I do this, you will see some noise naturally occurring. It's not going to be exactly the same, but a lot of them you can see are overlaying very perfectly. And I can remove that, and you may start to see some areas differing. So right in here, I'm looking at like there's some difference. And I'll take away persistence mode to clear it. All right, so now while I get on with the rest of the presentation, let's just capture a few traces here. Say 1500, be safe. So this is just going to go in the background, inputting different data. You have to make sure that fixed plane check is unchecked, or it will give you the same data, which is no good at all. And it's just going to keep capturing. So we'll let that go, and I'll continue talking with the rest of the presentation here. Minimize that. All right. So that's sort of the cool demo part. And you've seen right on the screen there, I had this waveform acquisition. So you might say, well, what were you using? What would you normally use? This is a typical setup. This is when I'm doing work with the SASEBO G2, this is how I started. And what I've used is a very high speed oscilloscope, 1 gigasample per second. Sorry, no, the scope itself can go a lot faster. I'm sampling at 1 gigasample per second in this case. And I just have a power trace connected across a shunt and a trigger probe. So why we need that high speed is I'm attacking a hardware device there that's running at 24 megahertz. And when you look into literature, you'll see that other people, this isn't, just, hey, I had a nice lab. It's frequently, especially for hardware implementations, they're finding that you need this minimum, this 250, 500 megasample per second for attacking, hardware running at moderate speeds, 12, 24 megahertz type thing. If you attack a software implementation, you can get away with a bit slower, like 100 megasamples per second, which is sort of $1,000 range. But it's still not ideal. So the question is, how can we get away with cheaper hardware, like what I have here? And the answer comes from, you remember how I said, right at the clock edge is when those lines are switching. So when we look at the power consumption is always synchronized perfectly to the clock edge. And this means what we really want is we want some specific point. It might be this point, it might be this point, but we always want to sample at that same point. If we sample off that point, that's bad. So if you're only sampling at 200 megasamples per second, you're not going to get that perfect sample that's consistent for every clock cycle, especially for these hardware implementations when we only have 10 or 11 cycles that we can use at all. We need to make sure it's consistent. And it may be that there's only one point you even really need, but you can't, which it actually ends up to be the case for a lot of these, but you need to make sure that point was just at the right time. And to do this, we just sample really fast and throw away everything that was wrong. So instead, what I've sort of done here. And what you can do with some oscilloscopes support this, most don't, but you sample synchronously. So you take the device clock and you say, use this transition here to decide when to sample. And you'll always end up sampling at the perfect moment. The thing is, now you're sampling based on when the device itself is going to be moving data around. And that's the real advantage of this technique. And I actually sample at 4 times the clock of the device under attack. There's no actual need to do this. It looks better is the reason I give you, because if you imagine sampling here, say these red dots are showing the sample, what you'll see is you'll just see this line because you're going to connect them. And that's it. And, you know, it goes down after. So that doesn't look very good. You go, oh, did that work? I don't even know. So the point is that if you do 4 times sampling, so you're sampling here, let me just clear all this. You won't see all these little nuances, but you'll at least see the generic shape of the waveform. So when you look at the sample, it'll look something like that. And you can say, ah, yes, my device is running. So I sample it 4 times solely for that reason. The other thing I briefly mentioned when I did that demo is we have this phase shift property. What's that about? So what this is about is showing you relative to that clock, we may want to sample right there, but that might not be good because we're right on the very brink of this point. And it may be that where we care about is somewhere, you know, further down the waveform. We may want to sample right here. So we add this delay between whenever the actual clock edge was somewhere back here to where we sample. This also accounts for problems like the ADC itself, the analog to digital converter, and parts of the digital board will add delay in naturally. So you may need to counter for that. For some devices, it really doesn't matter, but what I've seen is for some devices, it matters a lot. And there's an example. You can see some waveforms measured at different phase shifts. So you can see here, we've sort of bottomed out on part of these waveforms. We've thrown away this information. If we use a different phase shift, we get sort of nice, clean edges for that part of the waveform. So the capture hardware that I'm demonstrating here, this is to give you an idea what's involved in it. And you can see more about it in this other paper referenced here. So some of the interesting thing, we have this clock in. So this is from your device under attack. We have a clock multiplier, that phase shift I mentioned. We have an option of using a regular 100 megahertz clock. This is, when you're using that, it's basically a cheap oscilloscope-ish. A big difference is we have this amplifier at the input. So the hardware I'm showing is designed to measure very low signals. You can't, if you put 100 volts in, you know, it's just going to blow up. It's not like your oscilloscope. You can do that. The maximum, it sort of maxes out at something like 900 millivolts peak to peak. So it's designed for measuring the smaller signals that we often see. On the plus side, you can put a lot of gain. You can put 40 or 50 dB of gain right at the front end. So you can connect probes directly to it, like magnetic field probes. I'll talk about it later. It also gives you a FIFO, first in, first out buffer for sending data to the computer. And if your FPGA board supports it, what I've designed is just the analog part. The FPGA part depends on the board you use. But for example, you can pretty easily add DDR memory, and this means that now you can store something like, 32 or 40 million samples on the board. This is actually very handy if you are trying to characterize a system that you have no idea when the encryption is happening. So you need to sample over a long time. And remember, because you're sampling relative to the source clock, you're already doing yourself a favor by throwing away a lot of information you don't need. Here I'm keeping 4 samples for every clock cycle. You can go down and just keep 1 often if you want. So that's a photo of actually sort of the older green version. The new ones you'll see are red. And again, we have the OpenADC is my capture hardware on the top here in green. This photo is good because they are different colors for that reason. And the red board on the bottom is a $90 FPGA board that I just bought from Avnet. It has a Xilinx Spartan 6 LX9 on it. So, as I said, the big thing here is that design is totally open source. So we can use it in an oscilloscope-like mode, which is pretty standard. But the real advantage is that you can synchronize to the sample clock of your device you want to attack. And this really means you can attack high-speed targets well. So in the associated paper I have showing this board, it's showing you that for the SASEBO G2 running at 24 megahertz, this board is doing just as well as my 1 gigasample per second oscilloscope. And so this means it really gives you the ability. You're not doing sort of a half-assed attack that only works on slow software implementations. What I'm showing you is that, hey, you can use this for real devices doing, running at real frequencies, 24, 16 megahertz, anything. It also has the built-in amplifier, which makes it a little easier to work with. You just don't need as many things. So one thing you'll probably quickly say is, well, that's great, but with all this side channel stuff, you're using a shunt, which is cool, and it's very interesting that you're able to do this, but the fact is you've now taken this IC, you've done a bunch of modifications to the circuit board. How realistic is this? Am I really, people are going to do this and then somehow use it without getting noticed, or what? And the answer to that is that the basic idea of monitoring the data line switching is what we're doing. The basic idea isn't to use the power, despite the name. And we can pick up those switchings in a whole bunch of other ways. It doesn't have to be just a resistive shunt. We can use actually an electromagnetic probe, and we just put the probe near the chip. There's even cool demos I've seen with CRI, for example, doing a magnetic probe over a regular smartphone, and it works through the smartphone casing. So it's definitely not the case that you need to modify the hardware. And if you want to play with magnetic field probe, you'll need a magnetic field probe. It should not be, rocket science that you'll need one of these if you want to play with one of them. So if you go and you look at sort of what's in literature and you say, okay, I'd like to buy one, again, fairly expensive and not necessarily suitable for someone who's just interested in it. So there's a number of manufacturers. The price is always very similar, around $25K for a big set. You can buy individual probes for a little less, and some have some smaller kits that are a little less. But if all you want to do is look, there's not a need to go through that much effort. So what I'm going to show you is that you can build one on your own with a piece of semi-rigid cable with a SMA connector. And I bought these from eBay, I believe, or somewhere, but you can get them for cheap. There's tons of them around. And there's examples showing you how you can turn these into probes. So there's a great website it should all be linked from the white paper that's on the CD, or you'll have a copy of this too. And you basically just turn it into a magnetic field probe by looping it around, soldering on itself, cutting a slot. I wrap it in tape to avoid shorting out the board I'm testing. It's probably a good idea. Or you can use some Plasti-Dip stuff that should work. I've never found it locally. So when you're doing it, all we do is we just put the probe near the device we're attacking. So it is a very simple way to do this. And if you want, as I said, there's this reference which talks about how they're built, and actually some other ways to build them. And there's a very good thesis showing you about the probes for side channel analysis, and it specifically goes through a bunch of different tests of taking different probes and using them just for side channel analysis. So that's also a very good reference. When you use the probe, you'll see, hey, there's a pre-amplifier on this. So you need that preamplifier if you're using a regular scope. If you're using the OpenADC, you may not. You may still need one. I'm not going to guarantee the gain is going to be high enough on just the board. So for a preamplifier, instead you can just purchase generic preamplifiers, which look suspiciously similar to some of the ones that are sold with these magnetic field probes. I'm not going to say they get rebranded, but it looks maybe like that's what happens. And the specs are the same, so highly suspicious. But Mini Circuits is one example of a manufacturer of sort of off-the-shelf RF modules that sells such a low noise amplifier, and they have very nice characteristics, flat gain over wide frequency. But if you're too cheap for that, or you just don't want to bother, you're just playing around, you can actually buy these handy amplifier chips, monolithic amplifiers, and they're quite nice, very easy to use devices, very cheap, sort of $2. This is the Mini Circuits example again. I like using them, but there's other companies that may be easier to find in your local market. I have some of those listed in the data sheet, in the white paper. So there's example evaluation board schematics, and the evaluation board is a simple amplifier, so there's not much to it. Resistor, inductor, capacitor, the device, and you apply power, and that's it. So we can build it, and this is all it looks like. So I have some of the parts there. I have the resistors, the inductors. The inductor is there. So these are the resistors. Power's coming in. I have a voltage regulator mounted on the bottom you can't see. And there's actually two of them here, which is a bad idea because you get cross-coupling. So what I don't show you is the shield that goes in between these two. So here's the little amplifier chip. And the capacitors are just right on the ends there, so you can see some of the capacitors there. There's another guy there. So it's very simple to build one on your own and very cheap, and hey, it works pretty well. So here I've wrapped the whole thing in copper conductive tape to give it a bit of a shield, and then use non-conducting tape over everything so I don't short stuff on my workbench. So this is the gain measurement. It's around 30 dB. It's sort of hard to see. Unfortunately, this figure doesn't give me very high resolution. But you can see it's more than sufficient for what we're doing, because we are just trying to boost a signal a bunch so that we get a better results. The other thing you're likely to see is a differential probe. So here I pulled real scientific, or real paper. Someone's attacked the XMega crypto engine. Very interesting read. And one of the things they've done is they've used differential probes, and this you'll see very often. So a differential probe is helping with some of your noise characteristics because it's just measuring the voltage across the shunt and typically applying some gain to it. So if you have a regular scope that doesn't have a lot of gain at the low side, this is great because it solves sort of two problems at once. So hey, let's look at the probe in that paper. I want to replicate this. Well, it's a very nice probe, 1 gigahertz bandwidth, active differential probe. But, it's 4.5K, so that's fairly expensive. But we don't need 1 gigahertz bandwidth. 200 megahertz is more than enough, and we could go lower than that even, but they only sell one with 200 megahertz. But that's still, over $1,000 just for the probe. And you can get some used for a little bit cheaper. But to keep with the real cheapskate side to this talk, I mean actually cheapskate, what you can do is you can actually build a probe using some of these low-cost differential receiver amplifiers from analog devices. So your entire cost is going to be something like $5, maybe $10. It depends a bit what you might have in your parts bin at home. And it works well enough. It's not perfect. But as you can see, we can use this to actually attack targets that otherwise we may not have had quite as good results. There's more details about the probe construction in the white paper, though, if you are interested. I'm more just trying to show you this is one option instead of buying a very expensive off-the-shelf probe. So, what I want to do here is sort of wrap up a few other loose ends. When you're doing this, if you want to follow along, I ran this one example here that completed. And what you'll notice, though, is that the results you'll see will depend a bit on what type of device you attack. So here I have the AVR, the same board, and I've loaded it with 3 different AES implementations. This firmware is not on the CD. You'll have to go to my website to get the link to this. It wasn't quite ready in time, and I wasn't sure about distributing some of this on the CD itself. But what you see is that here's this AVR CryptoLib. I've just chosen 3 libraries that when you Google AVR AES, they come up as some of the first ones. So this AVR CryptoLib in C will look something like that. And we can sort of see these, you often will look for these hunks indicating, so you can see these are all the same here. So you can guess these are different rounds. You can see another one starting. This is a straightforward, I call it, implementation, and this is like a very textbook implementation. This comes from, again, I googled AVR AES, and one of the second or third hits is this C implementation taken from a course website, and again you can see some of these rounds. This AVR CryptoLib also have an assembly version which is much faster. So what you actually see is, again, here are the rounds, but they're occurring, they're done much quicker than in the C version. So the entire encryption has taken place in this small time span there that in the C version only a few of the rounds of AES has. And it also looks different depending on hardware. Here's an XMega, so that same AVR CryptoLib, and it looks quite different. The XMega is also a lot more dependent on the phase shift you use. This is one of the targets that you have to be careful with. XMega also has a hardware AES, and again, it goes much faster. It's completely done in sort of, few hundred clock cycles. Some other interesting things. You can also use the same hardware. There's a SASEBO board. This is a little more expensive. It's getting towards the higher end, but the SASEBO project has a number of sort of standard evaluation boards for side channel analysis, and they're very high quality boards designed specifically for this. So they have the reader and everything set up already. This OpenADC you can actually plug right on conveniently. It turns out it wasn't originally designed explicitly for this, but the OpenADC was designed to be flexible enough to work for applications like this. You can have this complete, nice looking transportable design. And the cool thing is this FPGA here is a huge one. If you know, it's Spartan 6 LX150. So you can either store a lot of sort of traces right on the FPGA, and you can even do processing on the FPGA if you really want to get into doing some of these attacks in real time. So before I sort of finish off, I'll just do one more thing here, and that is to show you I finished this capture, and what I'm going to do is I'm going to copy, and it just takes me a second here to get the capture software up. So I'm going to take this capture I just did right now, and this text in and wave I'm going to capture to this attack script that you have, and copy and replace. And this is all real, so this might fail. I hope not. And what we should see, if this worked, is we'll get the right encryption key. So we'll get this 2B, and I've just put the actual key for convenience sake in the source code. So it's actually figuring this out based on the acquisition you just saw running. So it's looking good, 2B, 7E, 15, and we should see it go through the whole thing. So I'm just going to finish this off, and we'll come back and see. So if you're interested, check out the white paper. Obviously, that has all the details, buying guide with a lot more about, hey, here's the different ways you can get involved. If you already have a scope, you may be able to use it. There's a few commercial scopes that have synchronous ability. This isn't the trigger. Remember, the trigger on the scope is just triggering the internal time base. Some scopes let you input a clock and sample on that. There's this great book I sort of started out with myself, and it goes through a lot of basic stuff, and the book website has some example MATLAB codes. There's the original DPA paper by Paul Kocher is pretty interesting. It's very straightforward to read, actually, so I always just recommend to start there. There's several conferences. You can look at the proceedings of them. If you don't have access to any of this, little hint is that a lot of universities will have some sort of research access. So if you access from their network, and they often have a computer in the library you can get at, you can get that. So I've been working on this in a few different aspects. You're at this intro presentation. In Blackhat Europe, I'm going to have a more detailed open source attack platform demoed rather than just this simple script. And I also have some designs for, you saw these hardware targets here, basically to give you the complete design for PCBs and everything, so you don't have to build them yourself. And that's sort of the whole package. Then you'd have everything. And pending, I was going to apply to Las Vegas Blackhat. So let's take a look at our script before I move to the last slide here. And there we go. So it worked, in fact, completely. It's printed the actual and the real key. So there is a live demonstration of differential power analysis attack performed on a few $100s worth of hardware. Thanks for attending, and you can email me if you have any questions.